This is part 14 of the series Calculus Prerequisites, and we're going to start this part with composite functions. And the definition of a composite function, let's say f and g are functions. The function given by f composed of g of x is equal to f of g of x is called the composite of f with g, or f of g of x. The domain of f of g of x, or f composed of g, is the set of all x values in the domain of g such that g of x is in the domain of f. Now I know that definition sounds really cryptic, but it's not as hard as it looks. Let's say that f is 2x and g of x equals 2. Well, f of g of x is just the same as saying I want to evaluate f at the values of g, which tells us that these values have to be in the domain of x. In other words, x has to be able to be evaluated at these values. So that equals 2, and wherever I see an x, I want to replace that with whatever g says. So that's a 2, which is 4. And it would be the same if g of x was some other function. Let's say that g of x was x plus 3. So this would end up being 2 times, wherever there's an x, I replace it with whatever g is, and that becomes x plus 3. So this becomes 2 times x is 2x, 2 times 3 is 6. So f of g of x with g being this would be this function. That's all it is. That's all we're talking about. So let's take a look at some examples and see if we can't work through them. So I'm given that f of x is 2x minus 3 and g of x is cos x. I want f composed of g, or basically what I'm saying is f of g of x. So I'm going to evaluate f at g of x. So I start with a 2. Now I have an x, so I'm going to replace that x with whatever g is. So that becomes cos x minus 3. And the result is the same. It's 2 cos x minus 3. That's f of g of x. Now g of f of x is just the reverse. I'm going to start with this. So I'm going to start with cosine, and wherever I have an x in this function, I'm going to replace it with whatever f is. So that's going to be 2x minus 3. So that's g of f of x. And the last one here, this is going to be a very familiar expression to you when we get to calculus. This is called the difference quotient, and it's going to be extremely important. We want to evaluate g of x, and f is x squared plus 2. So we're saying f of x plus delta x. So everywhere we have an f, we're going to evaluate it at x plus delta x. So we have x squared. So everywhere I see an x, I'm going to replace it with this. So I have x plus delta x squared plus 2, that's f of x, minus f of x, which is x squared plus 2. I'm evaluating f at x, so I'm just putting an x where an x belongs. And that's divided by delta x. Now, to evaluate this thing, I'm going to have to simplify, so I'm going to have to expand this binomial. So that gives me x squared, this times 2, so that's plus 2x delta x, and this guy squared, plus delta x squared, plus 2, distribute the negative 1, minus x squared minus 2. And that's all over delta x. So now we can simplify here. This x squared disappears because of that. This 2 goes away because of that. We have a delta x here, and every one of our remaining terms, this term, and this term, have a delta x in them. So this one goes away, one of these goes away, and this one goes away. So what I'm left with is 2x and a plus delta x. So that is evaluating g with these values. And that's function composition. So next, we're going to look at inverse functions. Okay, for inverse functions, recall that if a function h is the inverse of f, then f of h of x has to equal x, and h of f of x has to equal x. And that's because of the reflective property of inverses. That is, h and f are reflections across the line y equals x. So let's take a look at an example and verify that two functions are inverses. Here we have f of x is 2x to the third minus 1. G of x is the cube root of x plus 1 over 2. So let's first take a look at f of g of x. So that's 2. The x value, this goes in. So it's going to be the cube root of x plus 1 over 2 cubed minus 1. Well, this and this cancel out, so that's 2 times x plus 1 over 2 minus 1. This and this cancel out, that gives us x plus 1 minus 1, so that equals x. Now let's look at g of f of x. So we take this one, and that's the cube root of x, so we put in this wherever x is in this one. So that's 2x cubed minus 1 plus 1 over 2. Well, here we have negative 1 plus 1, that goes away. So we have the cube root of 2x cubed over 2. These 2's go away, and the cube root of x cubed, these cancel out, and we have x. So yes, in fact, these two are inverse functions of each other. This is a function, and it is the inverse of this. This is a function, and it is the inverse of this. It's important to note that a function may have an inverse, but that inverse may not be a function. So it's important to understand that. And so let us now move on. Now the last topic I want to review is the idea of trigonometric identities. Trigonometric functions play a major role in calculus. And so it's important that you understand all the basic trigonometric identities, and you can recognize them, at least in part, on inspection when you look at a particular function. It's going to be kind of critical that you can do that. So the more familiar you are with these, the better off you're going to be. So I'm not going to go through these in great detail. You can study these on your own, but the critical ones are the Pythagorean identities, the cofunction identities. Of course, these should be automatic, the fundamental identities. You need to know the sum and difference, the half angle. These are a little more obscure. We don't really encounter these a lot in Calculus 1, but it's not going to hurt you to know them. And the double angle, those are a little bit more frequent than these, but not too much more. But it's really important that you understand these top ones and the half angle identities. And the important thing to understand with all of these is that if you know the sum and difference identities, all these other identities can be derived from these. So I personally don't memorize these guys. I haven't got them all memorized, but I can reproduce all of these fairly quickly just using the sum and difference identities. I do have these memorized. So that's just an aside there. Now, from a graphical standpoint, we have the graphs of the functions and the unit circle. Now with this, the important thing to understand is you need to know the domains and ranges of all these trigonometric functions. It's very important that you understand how these things operate, and it's not necessarily critical that you can recognize the graphs, although it's going to be helpful for you. The important thing to understand is what are the domains and ranges of these different trigonometric functions. And again, they can all be derived. Arc sine can be derived from sine, and arc cos from cosine, and so on and so forth. But it's important to distinguish these and understand their differences. Now, you'll notice this expression, and this expression. I've provided those because most calculators, even graphing calculators, don't have the ability to do an arc cosecant, arc secant, or arc cotangent natively. And so to simulate the arc cosecant, you would do arc sine of 1 over the value you're trying to take the arc cosecant of. Here the same thing with arc cosine, and this one is just a 90-degree shift for arctan. So arc cotan is a 90-degree shift of arctan. So those are things that you need to have in mind. Now what we are going to do is go through some identities just to give you an idea of what you're going to have to be able to do from a manipulation standpoint. In each of these examples, our goal is to manipulate the left side to make it equal to the right. So let's start with this one, and we're going to do this with trigonometric identities. So we're going to change this secant. So we have sine x, and secant is 1 over cosine x. Well, sine divided by cosine is simply tan x. So we've manipulated the left side to equal the right side. Let's do the same thing with this guy. Now we're going to need a cosecant squared on the right, so we're going to leave this one alone. We're going to manipulate this guy. Well, based on the Pythagorean identities, we know that cosine squared x is equal to 1 minus sine squared x. So cosecant squared x times 1 minus sine squared x. And now we're going to multiply through, and we have cosecant squared x and minus cosecant squared x sine squared x. So we're getting closer here, but we've got this problem here. Well, cosecant squared is just, cosecant is 1 over sine. So this is cosecant squared x minus sine squared x over sine squared x, because 1 over sine squared x is cosecant squared x, and this is just 1. Cosecant squared x minus 1. So now we've changed this to that. And let's move over to this one. We're going to use the Pythagorean identities again. Secant squared x is tan squared x plus 1, and cosecant squared x is going to be 1 plus cotangent. And then when we simplify this, we have these 1's cancel out, and we're left with tan squared x minus cotan squared x. For this last problem, we're going to use a fundamental identity, and we're going to say that sine x, cotangent is simply cos x over sine x. Sine x divided by sine x is 1, so we're left with 1 over cos x, and they're the same. Well, I hope this helped out. This, again, is by no means comprehensive. You should review all the things and practice those things that you found difficult, and practice your trigonometric identities, and that will wrap up this series. And I will talk to you in the next series.